Welcome back, statistics scholars. Today we're going to be doing something a little different in terms of inferential testing. We're still going to be doing something that's called parametric testing, meaning an analysis that's of the mean. Parametric means of the mean. But we're no longer going to be asking the question that we've been asking all the way back since we were doing z-tests. With a z-test, we were comparing two averages, a sample average to a population average, x bar to mu. In the one sample t-test, we were comparing x bar to mu again. In an independent samples t-test, we were comparing two sample averages to two population averages according to the null hypothesis. In a paired samples t-test, we were comparing the average difference between pairs, so an average, to a null hypothesis average difference. So we were always asking the same question. Are these averages the same or different? It was the same basic question. I've got this average over here. Is it the same or different from this other average over here? But today we're going to be talking about correlation and covariance, which also is going to be dealing with the average, but the kind of question we're going to be asking from an analytic standpoint is really quite different. Because now, instead of having groups where we're asking, is this group different from this other group over here, we're going to be looking for patterns between two quantitative variables. Before, we only ever had one quantitative variable, right? Height, weight. Let's say let's use the independent samples t-test as an example of what we were doing before. We might ask, are men different from women in terms of height? So we've got two groups, men versus women, one qualitative variable, gender, men versus women, and now we're comparing them on some quantitative dimension. So we're going to look at the height for men and the height for women, but it's still one variable where people can differ in terms of dimension, more versus less, amount. But now we're going to be asking, well, what happens if we have two quantitative variables? Can we still look at patterns? Can we ask interesting research questions when we're dealing only with quantitative or dimension-based variables? No groups anymore. We're not looking at group differences. We're not looking at qualitative, categorical, group-based variables. Now we're only looking at quantitative variables. And so the type of analysis we do and the question that we ask is a little bit different. So, to refresh your memory, whenever we're dealing with quantitative data, we're dealing with variables, a way that people can be different from each other, where people are different in terms of amount, where bigger numbers mean a person has more of something, right? And if an average is higher, that means that there is more of that, right? So bigger numbers mean more of whatever it is you're measuring, like height. Bigger numbers would mean you were taller. Reaction times. Bigger numbers would mean you were slower, that you took more time to do something. Depression. Higher numbers would be a bad thing because it would indicate you have more depression. Well-being. Higher numbers would indicate you have greater well-being, and so you're better off. Either way, on a quantitative variable, people differ in terms of amount. Hopefully this is review for you at this point. Well, and before we were dealing with quantitative data. We were dealing with one sample of quantitative data in a one sample T or Z test. In an independent samples t-test, we were looking at two samples of quantitative data. And the samples were different based on some group-based variable, like height for men versus height for women. One quantitative variable, one qualitative group-based variable. But now we want to ask a different question. We want to ask, is there some pattern? Is there some systematic relationship in one group of people when we look at two of their quantitative variables? We ask this question. When we look in one group of people, so we're back in one sample land, right? One sample land that's allowing us to make a decision about one population. When we look at one group of people, is there some systematic relationship between how people fall out, people's outcomes on two quantitative variables? If people tend to be high on one variable, are they high on the other? If people are high on one variable, are they low on the other? If some people are high on one or low on the other, is there some systematic relationship between these two variables? Let me give you an example. Because let's say I'm looking at height and weight. Height is a quantitative variable, and so is weight. And there is a systematic relationship between them. If I look at one group of people, one sample of people, I'm betting I'm going to find that the people who are taller are on average a little bit heavier than the people who are shorter. It's probably not going to be a perfect relationship, but there's going to be some systematic relationship there, because the taller you are, the more mass that you have, you're probably going to be a little bit heavier on average. When you look at all of the people together, the taller people are probably going to be on average a little heavier than the shorter people are going to be. Of course, there are exceptions to this rule, but it's about the pattern. It's about what's happening on average. So there's that average word again. And again, correlation and covariance are parametric analyses of the average, but we're not looking to see if the averages are different between two groups anymore. Rather, we're looking to see if the people who are above average on one variable are systematically above or below average on a second quantitative variable. And so it just changes the kind of question that we're asking. And what we're going to do over the course of today's lecture is we're going to be exploring scatterplots, which are ways to visually wrap our head around the idea of quantitative analysis, where you only have dimension-based quantitative variables where people are different in terms of amount. So scatterplots are about a visual representation of the relationships. Then we're going to learn how to calculate covariance, and we're going to learn how to calculate correlation today. And next time, we'll learn about an extension of the correlation called regression. So let's begin with a scatterplot. Now, a scatterplot has an x and y axes, just like all the other plots that we've looked at this semester. We've looked at histograms at an x and y axis. We looked at a density plot, which had an x and a y axis, and a scatterplot does as well. But what goes on the x and y axis are a little different. So you've got this empty graph with an x and y axis, these lines, right? Let me draw one for you. So you've got this axis. Here's the x-axis and here's the y-axis, right? Well, instead of putting like frequency on the y-axis, rather you put one quantitative variable along the x-axis, and then you put the other quantitative variable along the y. And as you get close to where they intersect, that's where you're going to have none of the x and none of the y, right? So let's say you put height along the x-axis. As people get taller, you're going to track where they are along the x-axis. And let's say you put weight on the y-axis. As people get heavier, you would then track them along the y-axis. And then where somebody is in terms of both their height and their weight, x and y-axis, you put a dot. So that's person 1. And here would be person 2, and person 3, and person 4, and person 5, and person 6, right? And so you would create this cloud of dots that represents where everyone is on their height and weight. You can use X's or dots or whatever. And you do this for every single person in your data set, and you end up with a cloud of dots. And so here is a much better drawn scatter plot. It's a scatter of dots, right? It's a scatter of dots. And so here I have a variable that ranges from -3 to +3. And here I have another variable that ranges from -3 to +3. Let's say this is how much people love carrots and how much people love beets along the x and y axis. And what you can sort of see here visually is the people who are feeling quite strongly about carrots. Let's put carrots along the x-axis. How much people love carrots along the x-axis. And let's put how much people love beets along the y-axis. Try to draw a little beet here. Right? You can see that the people who are saying 3, 3, 3 are also the people who are saying kind of a high for beets. There are exceptions to the rule. But in general, I'm noticing that the people who are above average on carrot love, -3 to +3, are also the people who are above average on beet love. People who are below average on carrot love are also the same people who are below average on beet love. People in the middle are generally the people in the middle. Lots of exceptions to this rule, but I can sort of see this pattern. And I can see that with the scatter plot. But people are bad at eyeballing these plots, right? People are not very good at it. Even though the scatter plot can give you a general sense of how two variables might be related, we want some numerical index of how related two variables are. Because what we're really asking ourselves is, there are people who are above average. There are people on a particular variable, like how do you feel about beets? How do you feel about carrots? Are those the same people who are above or below average on a different variable? And we can look at a scatter plot like this and get a visual sense of it. I sort of notice that these dots are clustering in a meaningful fashion. We want a way to numerically represent this cloud of dots. We're looking for what's called the covariance. And this is all about variability. We're asking if someone is above or below average on one variable, are they also above and below average on a second variable? How are they varying around that average? Above average versus below average. And if you think back to this, and so we're going to work from what we already know, right? We're going to work from what we already know, because we're asking this question. As scores on one variable go up, what happens to the other variable? As people tend to be above average on one variable, is there some systematic relationship on the second variable, like height and weight? People who are taller on the height variable are probably going to be heavier on the weight variable, right? That's asking about the variation in height compared to the variation in weight, right? So we're going to work from what we already know about the variance. We're going to go back to that variance equation and notice something about it. This is the variance equation here, right? There's that symbol for the sample variance. And we notice that when we calculated the variance for one quantitative variable, we looked at how each person X was different from the average Y. So how in one variable people varied within itself. So we can actually think of the variance is how a single variable varies within itself, or how much people are different. So let's just take height, right? Height has a lot of variability, you know, in adult humans, ranging from people who are very short, 2 or 3 feet, to people who are very tall, much higher than 7 feet. There's a lot of variability within the one variable of height. And so we look at this equation for the variance. I'll highlight it for you here. Because this says on one variable, how much are people different from each other, right? In one variable, how much are people different from each other? Well, I'm going to rewrite that equation like this. And this is where that prerequisite math will come in handy. Because not that we'll be foiling in here, but notice that I can rewrite this part of the equation, x minus x bar squared, like this. Because what is squaring really? It's taking something and multiplying it by itself. So I'm taking x minus x bar and multiplying it by itself. And these two equations then become mathematically equivalent. This is just another way of writing the variance equation. X minus x bar squared, x minus x bar times x minus x bar. This gives me how much within a single variable, a variable varies within itself. Well, let me borrow this equation, because what I want is not how much a single variable varies within itself, right? That's what the variance is. It's the spread in the data. Are people very spread out from each other or not very spread out from each other? Think back to what the variance is. It's the amount of variability in a single variable. That's where that name comes from. In a single way that people can be different, how much variability is there in that one variable? But now the covariance, this is something different that I want. I want to know, based on whether or not someone is above or below average on a single variable, how does that relate to how that same person is above or below average on a second variable? So I'm going to borrow this variance equation and I'm going to turn it into the covariance. Ta-da! And here I get the covariance. I look at how each person X on the X variable, let's call this height, how they're different above or below average on the height variable. Then I'm going to compare that to for that same person on a Y variable. So on a second quantitative variable. So I'm not going to call it X anymore. I'm going to call it Y because it's a second quantitative variable. So now X is height and Y is weight. And I'm going to look for each and every single person. I'm going to go, okay, here's the X variable right here. How is this person above or below average on the X variable? Then for that very same person, I'm going to look to see how that person is above or below average on the Y variable. And then I'm going to multiply those two numbers together. Because if they're above average on X and they're above average on Y, I'm going to end up with a positive number. Also, if they're below average on X and below average on Y, I'm also going to end up with a positive number. In this way, I can mathematically explore how the variation in X is related to the variation in Y, the covariation. And then after I've done all these multiplications, this is called cross-multiplying. When I get all the deviation scores for X, then I'm going to get all the deviation scores for Y, then I'm going to cross-multiply them. After I get all those multiplications, I'm going to add all those up, and then I'm going to divide by n minus 1. And the symbol for covariation can either be cov xy as the subscript, or it can be s sub xy. I prefer cov sub xy because then it's really straightforward and simple. I just know COV sub xy is the covariance. It's right there in the name. But there are other symbols out there like s sub xy, and you should be familiar with them. Right? And it really is just a mathematical extension of the variance. It really is. We're just looking for the variation in X versus the variation in Y. The variation in people's heights versus the variation in people's weights. It can be anything. It's based on the raw units, so that's what the units of measurement are. It's based on the raw units, and so theoretically it's unbounded. That means your covariance could be any number. It ranges from positive infinity to negative infinity. And so it can be any number. But we have a number that represents the covariation between two quantitative variables. All right, so let's work through an example using height and weight to wrap our head around how to calculate the covariance and what the covariance is really looking at. So here is some data that I made up for a group of 4 people. So we've got participant 1, participant 2, participant 3, participant 4, right? I have that right here. And the first person has a height of 64 inches. So I'm measuring height in inches. That same person has a weight of 146 pounds. So I'm measuring weight in pounds. So those are the original units. Height in inches, weight in pounds. The second person has a height of 68 inches and a weight of 180 pounds. Third person, 74 inches and a weight of 200 pounds. Fourth person, 62 inches, 150 pounds. And so X is my height variable and Y is my weight variable. And my total sample size is 4 because in the world of covariance and correlation, sample size is not the number of numbers you have, it's the number of people that you have. Sort of like in a paired samples t-test, where it was the number of pairs that you have. Here it's the number of people because we have 2 numbers for each person. So total sample size, big mama N, is 4. And I've gone ahead and I've calculated the average here for each. So the average of X is 64 plus 68 plus 74 plus 62 divided by 4, right, which is 268 divided by 4, which is 67. Then the average for Y, which I'm going to call Y bar, same thing as X bar except for the Y variable, is 145 plus 180 plus 200 plus 150 divided by 4, which is going to be 676. There's a typo there. My bad. It's 146. 100 plus 180 plus 200 plus 150 divided by 4, which is 676, divided by 4, which is 169. So my average for the x variable is 67, and my average for the y variable is 169. And what the covariance is asking, now that we have these averages, is there some pattern here where the people who are below average, below 67 on the first variable, are they going to be above or below average on the second variable? And will there be some meaningful pattern here where the covariance is going to be a numerical index of that relationship? And so so here is the covariance equation. And here is the first step in the covariance equation. The very first step is to get the deviation scores for x and the deviation scores for y, just like we did before when we were doing the standard deviations. So here is me getting the deviation scores for x. I take the average for x and I subtract it from the data. 64 minus 67, which is negative 3. 68 minus 67, which is positive 1. 74 minus 67, which is positive 7. 62 minus 67, which is negative 5. And unlike with the standard deviation, the sign very much matters. Very much so. Because if I end up with two negative numbers, that means this person here, person 1, is both below average on the first variable and below average on the second variable. That would indicate maybe this person has some pattern. People below average on one are below average on the other, like height and weight. If you're below average on height, maybe you're also below average on weight. But here's the second person. They had a positive number for the first variable and a positive number for the second variable, right? And the sign very much matters because this indicates that this person is above average on both. Third person, above average on both. Fourth person, below average on both. So now I've done this first step in this equation. So what's the next step? To get what are called the cross products. We're going to cross multiply across the x and y variables for each person. So for person 1, I take negative 3 and I multiply it by negative 23 to get positive 69. For the second person, I take positive 1 and I multiply it by positive 11 to get positive 11. Number 3, positive 7 by positive 31 to get positive 217. Because this person was really above average on both. Wow, this indicates there may be some real pattern here. Because look, this person was much taller than average and much heavier than average, making this very large cross product. And we have this next person who was very much below average and very much below average, right? This person was very much below average on both, giving me a large cross product, but a positive cross product. Because what has emerged here is that if you're above average on one, you're also above average on the other, height and weight. And if you're below average on one, you're below average on the other. And all four people showed this same pattern, which is why I get the same sign for the cross products. Now, what's the next step? Well, the next step is to add all these together. I've done this, I've done this, I've gotten the cross product, and now I'm going to add these cross products together. 69 plus 11 plus 217 plus 95, right? Now, let's say there had been an exception to this rule. Let's say there had been a person who was above average on one but below average on the other. I would end up with a negative cross product and thus a negative number down here, making this summation smaller, right? Because that would violate the pattern, making the pattern smaller. So I take this 392 and I'm going to divide by 3 because that is what the equation tells me to do, to divide by the degrees of freedom, n minus 1 in this case, n minus 1, right? And so then I get 392 divided by 3, which is, typo, 130.67. So 392 divided by 3 is 130.67. Sorry for the typo there. 130.67. That is the covariance between x and y, right? And it's based on the original units of measurement, It's based on the fact that I measured height in inches and weight in pounds. If I had measured height in centimeters and weight in kilograms, I would have had a different number here, right? But this is in the original units unstandardized. In the unstandardized original units of measurement, the amount of covariance between height and weight is 130.67. And so it's positive. It's a positive number. And you can interpret the positive number, but that's it. That's all that you can interpret. Because it's based on the unstandardized original units of measurement, all you can say is higher numbers on weight, go with higher numbers on height. Lower numbers on weight, go with lower numbers on height, and people in the middle on one, go with the people in the middle on the other, that there is a positive relationship here because the variables were moving in the same direction. High on one meant high on the other. Low on one meant low on the other, which resulted in a positive set of cross products and thus a positive covariance. But that's it. That's all you can say at this point. Because the covariance is going to be the unstandardized linear association between the variables. Now, why is it called a linear association? Well, because it's really getting at how well a straight line fits the data. More on that in a bit. But that is the formal definition of the covariance. It is the unstandardized linear association between the variables. And it can range from infinity to positive infinity theoretically, depending on what you're measuring, right? If you're measuring the distances between stars, right, we're going to be talking in light years, right? If we're talking, and it can be really any number because it's based on those original units of measurement because it is unstandardized. So other than the fact that it could be positive or negative, a positive or negative number, you can't really interpret it. And so you can't compare two covariances. You can't really interpret it. And so it's not all that great all by itself. It's nice because it's just a mathematical extension of the variance. It is a number that represents the unstandardized relationship between two variables. If it's a positive number, that means high scores on one, go with high scores on the other. Low scores on one, go with low scores on the other. If we had a negative covariance, right, that would have indicated that people above average on one were below average on the other. So we would have had a negative set of covariances, a negative set of cross products rather, and that would have resulted in a negative covariance. And that would mean high scores on one go with low scores on the other. So let's come up with an example for that. Let's talk about how much you weigh and the number of minutes you exercise, right? That might give you a negative covariance because higher numbers of exercise, right? The larger number of minutes you exercise in a week is probably going to go with lower weight. So high scores on one would have gone with low scores on the other, right? That would be a negative relationship because you would end up with negative cross products. And so you can only interpret in the covariance only the positive or negative sign. So it would be nice, would be fantastic, if we had some way to standardize the covariance, to take the covariance that we just calculated and turn it into a number that we can interpret, to standardize it in some way. How might we do that? Let's do it like this. This is the Pearson product moment correlation. And here is how you calculate it. And this is the symbol for it. The symbol for the sample correlation is R sub xy. And so then you take the covariance and you simply divide by the product of the two standard deviations. Kind of like when we did a z-score, we took the score minus the average and divided by the standard deviation, and that standardized it. I know, that was so long ago. That gave us a standard index. Dividing by the standard deviation gave us a standard index. Well, it's the same thing here with the covariance. Take the standard deviation for x and the standard deviation for y, and then divide the covariance by the two standard deviations, and that will give you a standard index of the relationship between the two variables, right? All you're doing is standardizing the covariance. That's it. Just like we used to standardize scores. So now we're in Z units, right? We're taking away those original units of measurement by dividing by the two standard deviations. And now we have something that we can interpret. And the correlation is then awesome because you can interpret it. Where were we? Right? So here's some things to know about the standardized linear association between the variables called the correlation. Here's some things to note about it. One, because you have divided by the two standard deviations, what's called mathematically bound it. Unlike the covariance, which could range from positive infinity to negative infinity based on your original units of measurement, the Pearson product moment correlation coefficient, such a mouthful, we just end up calling it the correlation. The correlation can only range from +1 to -1. It's what's called mathematically bounded. That is what happens when you divide by the two standard deviations. It, boom, can never, never, never be greater than +1 or less than -1. And so it's interpretable. It's a standardized covariance. And the way you interpret it is this way. Any number close to 0 indicates no relationship, nothing to see. Drive through. There's no systematic relationship between height and weight. Like, for example, let's say your test scores and your shoe size. I'm guessing if I tracked everyone in class's shoe size, there would be people who are above average on shoe size and people below average on shoe size. I'm guessing people above average on shoe size, there are people who do well and the people who do not do well. So no systematic relationship between where you are on shoe size and where you are on your test scores. It would just be a big old mess. There would be no relationship at all. And so the correlation that you calculate would be pretty darn close to 0. Any number that's either close to +1 or -1 indicates a strong systematic relationship, where if the covariance is positive, the correlation will be positive. And that means high scores on one go with high scores on the other. That as y increases, x is also increasing, like the relationship between height and weight. Or the relationship between your study times, the number of hours you plan on studying in your exam grades. People who are higher on study times are probably also higher on exam grades. And a negative covariance would indicate a negative correlation, and you would end up with something negative here. Like the number of minutes you exercise and higher would indicate lower weight, probably, on average. High scores on one variable go with low scores on the other. So as y decreases, x is going to increase. Sort of like the number of, like if you're in an in-person class. Or in our class, the number of assignments you miss. As the number of assignments you miss, quizzes, lab assignments, forum activities, as that goes up, the number of assignments that you miss, your test grades are going to go down on average. And that is how you can interpret a Pearson product moment correlation coefficient, just called the correlation for short. And so let's calculate it for this example. We've already calculated the covariance here, right? We calculated the covariance between height and weight, and we got 130.67. It's based on both the height and the weight, original units of measurement. Well, now let's standardize it so we can interpret it. We need to standardize it using this equation here. So let's do that. And the nice thing about the correlation is you've already calculated the covariance. So now the only thing you have to do left in order to calculate the correlation is calculate the standard deviation for x and the standard deviation for y. That is how you're going to calculate the correlation rather. And so I'm going to need the two standard deviations, right? In order to calculate the correlation, let's put that equation down here so we can see it. I'm going to need the two standard deviations. Well, happily, when I calculated the covariance, here is the equation for the variance, not the covariance, but the variance, because I'm going to need that for the x variable, and I'm going to need that for the y variable. I've already calculated the two sets of deviation scores. I already did that when I calculated the covariance. So I'm not going to recalculate them. I'm just going to borrow them, right? I'm going to say, oh, I already calculated the deviation score for x. I've already calculated the deviation scores for y. And so now I can get the squared deviation scores because that's my next step to calculate the standard deviation. Hopefully this feels a whole lot like review because we've calculated variances a lot all semester. So here I've got my deviation scores for x, my deviation scores for y. I just pulled those down from when I calculated the deviation scores when I calculated the covariance, right? Because let's go ahead and look at that equation from before, right? Here was my covariance equation. When I calculated the covariance equation, I already got the deviation scores, right? I didn't square anything. I got the cross products, but I did already get these two sets of deviation scores, which is fantastic when I want to then go and calculate the standard deviation. I square the deviation scores because that's what the standard deviation equation is telling me to do. So I square -3, +1, +7, -5 to get my square deviation scores. Now, why do I need this again? Because I need the two standard deviations to get my correlation so that I can standardize my covariance, which I calculated before using this. So now I've got my deviation scores for x. What am I going to do next to get the standard deviation? That's right, calculate the sum of squares by taking 9 + 1 + 49 + 25 to get 84. I'm now going to divide 84. I'm now going to divide 84 by 3. I just fixed a couple typos there, sorry. I'm going to divide 84 by 3 to get 28. And then I'm going to take the square root of 28 to get 5.29. Then over here for the y variable, I'm going to get the sum. I'm going to square all the deviation scores. These are my squared deviation scores because I'm just doing the same equation except for y. Technically, this would be y minus y bar, but it's the same basic form. It's just with the other variable. So I take -23 and I square it, +11 and I square it, on and on and on to get my square deviation scores. Then I get my sum of squares by adding 529 + 121 + 926 + 381. This is my sum of squares. Divide that by 3 to get 645.67. Take the square root of that to get 25.41. Now, I have my two standard deviations. And notice that I'm dividing by 3 because it's still n-1. The covariance for a sample, still you need to divide by n-1. So I've got my covariance for x, I've got my covariance for x and y. And now I've calculated the two standard deviations. Now I can plug those in to this equation for the correlation to get the interpretable correlation. And here is me doing that. Here was the covariance that I calculated before using this equation. We went through these various steps to get the covariance of 130.67. So I plugged that into the equation. Then I followed these procedures to get the two standard deviations, which is just review. We've done it a bunch of times, right? So I've got the standard deviation for x and the standard deviation for y. So now I plug those into the equation. I take 5.29, which was the standard deviation for x. I take the standard deviation for y, and I multiply them together. 5.29 times 25.41 is 134.42. Now I take the covariance, 130.67, and I take the product of the two standard deviations, and I divide. That's going to give me my standardized covariance, which we call the correlation coefficient, and it's 0.97. Extremely close to 1 because look at my data. If we go back to my original data, every single person who was above average on height was also above average on weight. And every single person who was below average on height was below average on weight. There was an incredibly systematic relationship. Higher scores on height went with higher scores on weight. And it was an almost perfect systematic relationship. So close to one, right? In real data, you never get this close. Just so you know, in real data, you never get this close. And so there is one more layer of interpretation you need to know. In psychology, now again, this doesn't hold for other disciplines, but in psychology, generally speaking, any correlations that range from 0 to 0.2 to basically 0.3, 0.29999 are considered small or weak correlations. Small. Anything that ranges between 0.3 and 0.4999999 is considered a mediate or moderate correlation, and anything above 0.5 is considered quite large, quite systematic. However, this varies a lot by discipline, right? So the correlation is not a substitute for knowing your variables really well, because in some disciplines, you want really, really, really high correlations for anything to be meaningful, like in the world of data validation. When you're doing what are called validation studies, you need your correlations to be at like 0.8, right, or higher. However, in the world of medicine, even very small correlations, right, can be very, very meaningful. Let me give you an example of that. The correlation between your risk of heart attack and whether or not you take aspirin, yes, no, is 0.08. So seemingly very, very, very close to 0. But this basically says if you do take, if you don't take aspirin, right, then your risk goes up. And if you do take aspirin, your risk goes down. It's a very, very small change in the risk, but when you're looking at thousands and thousands of people, it ends up being sort of a big deal, which is why they recommend you take aspirin if you have a family history of heart disease, right? So, but in psychology, anything below 0.3 is small, 0.3 to 0.5 is medium, and above 0.5 is considered large or strong. And you should know those rules of thumb. But sort of like Cohen's d, they're just rules of thumb. Just rules of thumb. So, next thing. I also want to teach you about something called R squared. The correlation acts as its own effect size, right? But often people will also report something called R squared. And all R squared is the correlation squared, literally. And so if you have a correlation of 0.5, then your R squared is going to be 0.5 squared, which is 0.25. If your correlation is negative 0.3, because you can totally have negative correlations, it means high scores on one go with low scores on the other. Like the number of assignments you miss goes up, exam grades go down. As the number of exercise minutes goes up, weight goes down, right? Negative correlation of negative 0.3, that would be 0.09. You just square it. And now you can interpret it a whole lot like an eta squared. Remember that from the ANOVA? You can interpret an R squared a whole lot like an eta squared. It is the amount of variability that one variable can predict in the other. And so let's say that there's a correlation. Let's use our example of height and weight. 0.97. Right? That is our correlation. To get the R squared, I would square that. So I take 0.97 and I square it to get 0.94 once I round. That means 94% of someone's weight can be predicted by their height. You switch that proportion into a percentage, and now you can say, right, we take that proportion of 0.94, turn it into a percentage, and you can then say 97% of someone's weight can be predicted by their height, can be explained by their height, right? And so that's just, it's something else that often gets reported as well. R squared. And what you can really think conceptually What a correlation is doing is sort of measuring the spread of the scatter plot. The correlation is a standardized way of measuring the spread in a scatter plot. And so let's take a look at some scatter plots and see how the correlation maps onto them. So here on the left would be a correlation of 0. Notice that when I draw a circle around this cloud of dots, I get a big circle. I get a big mess. Because let's look at the x and y axes here. They range from -3 to +3. And let's say this is, again, on a scale of +3 to -3. How much do you love beets? And let's say that's the x variable. And let's say on the how much you love, carrots, let's say is on the x variable. Right, so we've got our carrots down here. Dun, 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 dun. Right, and let's say on the y variable, we're asking people how much they like dogs, right? So we'll just, put a little heart here for how much you like dogs, because I like dogs, right? And so let's say there's no relationship between how much people like carrots and how much people like dogs. People who love carrots, there are some of them, right? There are people who like dogs, people who don't like dogs. People who hate carrots, people who like dogs, people who don't like dogs. Or let's say this is the relationship between your shoe size that I've made be from +3 to -3, whatever, right? Let's say I've transformed your shoe size. Or let's say this x variable ranges from, a size 5 to a size 14, whatever. There are people who score high on shoe size, people who score low on shoe size. And among these people, there are plenty of people who do well and plenty of people who don't do well. And among people with small feet, plenty of people who do well, plenty of people who don't do well. So there's no relationship here. And when I calculate the correlation, I get a correlation of 0 because there's nothing to see. And I would say there is no linear relationship between the variables. Because when I look at these cloud of dots, a straight line doesn't make a whole lot of sense, right? Because that's the other way to understand the correlation. The more it looks like a 1 or a hot dog, the more like a straight line the cloud of dots looks, the stronger the correlation is, the more systematic the relationship between the variables. Here we have a correlation of 0.25. A small correlation by psychology's standards, but you can sort of kind of see a trend here, that if you're high on X, you're ever so slightly more likely to be high on Y. There's nobody down here in this very high on X, very low on Y quadrant, right? There's nobody down here. There were people down here over here, but now there's not very many people down here. There were plenty of people up here, but not very many people up here. There appears to be what's called a linear trend. And I can sort of kind of imagine a straight line going through these data. I can sort of kind of imagine that straight line, which is why it is called a linear relationship. Here we have a much stronger correlation, -0.5. And notice that the tilt of my dots is now going the other way. And if I imagine a straight line through my data points, I can see that the straight line now goes the other way. For those of you who remember your previous math classes, these lines would have slopes, right? And notice that the slope over here would be a positive one to go with this positive relationship. And this imaginary line over here would be a negative slope to go with this negative relationship. And that is not a coincidence. There's a mathematical reason for that, which we'll go over in our next lecture. Here we have an even stronger relationship. There's almost nobody who is high on X, who is even remotely low on Y. Over here, it's a negative relationship. People high on X are in fact low on Y. People low on X are high on Y. It's just the opposite negative relationship, but it's still a fairly strong one, right? this negative 0.5 is a stronger relationship than this positive 0.25. Let's say this is the relationship between height and weight. Let's say this is the relationship between marital conflict and how satisfied you are with your marriage. As marital conflict goes up, marital satisfaction would go down, right? So anytime, as the number of exercise minutes goes up, your weight would go down. Here would be the relationship between the number of hours you plan on studying and your exam grades. People who study a lot are probably going to do better. People that don't study very much are not going to do as well, right? And so these are just some examples of scatter plots. And at the end of the day, the correlation is a numerical index of the strength of the relationship, right? And I'm not going to have you eyeball graphs on the exam, but just know that the tighter this circle is, the closer and closer and closer these dots get to this line, the less spread out the dots are around the line. I'll say that again. The less spread out these dots are around the line, the stronger that correlation is going to be. And in fact, let me just go ahead and draw for you what a perfect correlation would look like. So here I have my X and Y coordinate plane, right? If there was a perfect systematic relationship between my two variables, there would be literally a straight line that went through my data. That would be a positive relationship. As X goes up, Y goes up. As X goes up, Y goes up. As X goes up, Y goes up. Perfect relationship. And the correlation would be perfectly 1. You can have a perfect relationship in the negative direction. As X goes up, Y goes down. As X goes up, Y goes down. As X goes up, Y goes down. On and on and on. And if I drew a straight line through these data points, it would be a perfectly straight line, and the correlation would be a perfect negative 1.0. And that is how you can then interpret a correlation. The closer it is to positive 1 or negative 1, the stronger the relationship is. And so, the correlation is the standardized linear association between the variables. It measures how tightly packed around an imaginary line, so that's where the word linear comes from, how tightly packed around an imaginary line a cloud of dots is. But these dots are people. The more systematic a relationship is between two quantitative variables, the more tightly packed around this line the data points will be. Every single dot here is a person. It represents their score on the X variable and their score on the Y variable. And the closer everyone is to this line, the more systematic the relationship is between the two variables, the fewer exceptions there are. Just like I made this 4-person data set back here, where I made there be almost no exceptions. Every single person, if they were high on one variable, they were high on the other. I made myself something darn close to a perfect relationship, a perfect linear relationship, because I made up the data. Real data, of course, is much messier than that. Here I have a negative 0.5 correlation, but you can see the general trend. In general, if you're high on X, you're low on Y. There are exceptions to this rule, like these two people. These two people have the exact same score on X, but very different scores on Y. These two people have the same score on X, but very different scores on Y. So there are exceptions to the rule in this negative 0.5 relationship, but you can see this trend, right? Lots of exceptions, which is why the correlation isn't a perfect -1, but it's generally speaking a linear relationship. The more the dots look like a hot dog, the stronger the relationship. The more they look like a pizza, the weaker the relationship. Or you can think of this as the closer that dots look to a 1, the stronger the relationship. The more the dots look like a big fat 0, the weaker the relationship. And so And so here are some examples of positive and negative correlations, right? Here would be a positive correlation because higher scores on X go with higher scores on Y. Again, here is a negative correlation. Higher scores on X are going with negative scores on Y. But I'm showing you this because these two scatter plots have the exact same strength. They both have a 0.75 strength. This is a positive relationship. This is a negative relationship. They're both very strong relationships, right? Very systematic. It's just high scores are going with high scores here, low scores with low scores here. High, high, low, low. Here it's just the reverse. Low scores on X are going with high scores on Y. High scores on X are going with low scores on Y. Think of this as like, let's always say let's look at your exam grades, right? Let's say exam grades are here on the x-axis. And let's say your study times are along the y-axis. As the number of hours that you study goes up, so does your exam grades. Looking at a group of people, the students who studied a lot are also the people who did well. The people who studied not so much are not the people who did well. Of course, there are exceptions to this rule, right? These two people studied the same amount, but got different, right? These two people got the same exam grade here in fuchsia, but studied different amounts, right? But it's not, but it's still, generally speaking, a linear relationship. I can draw a straight line through these data. I can draw a circle around these data, and it looks example Same thing here. Let's say this is the number of, assignments you miss, right? If you, let's say this is the number of assignments you miss. Here we have people doing very, very well on the exam because they missed almost no assignments. People who missed many, many assignments did not do so well on the exam. There are exceptions to this rule, but generally speaking, if I draw an oval around these dots, it's more hot dog shaped than pizza shaped. This is approximating that one relationship. Now, so that's all the mathematics behind correlation. Now we need to talk about some theory, right? Oh no, back to theory. Yes, back to theory. And what we're going to talk about now is the fact that all of the language of correlation seems to suggest a cause and effect relationship. It's sort of right there in sort of the language of it. We can use the x variable to predict the y variable. As x goes up, y also goes up. But it's important to remember that the correlation can track any systematic relationship in the world. It does not necessarily mean there is a cause and effect relationship. Because just because two variables happen to move with each other in the world doesn't mean x causes y or y causes x. There's a phrase you're going to learn if you take any other psychology classes, and it is correlation does not imply causation. It's a hint. It's a suggestion. It's a little neon sign that flashes over here and says there might be a cause and effect relationship over here. You might want to check it out, but it doesn't necessarily mean that there is. That just because there's a correlation does not mean that there is a cause and effect relationship. That is actually a fallacy. It's called a logical fallacy. It's called the fallacy of post hoc ergo propter hoc for those who care about logic, care about philosophy. Just because A came before B doesn't mean A caused B. Just because there is a systematic relationship between two variables does not mean that there is a cause and effect relationship. Cause and effect is different than systematic. And this is kind of a tough concept to wrap your head around. Now, the idea with cause and effect is about direction. A causes B. B causes A. And oftentimes in the world of correlation, there's this subtle implication of cause, right? Like if you're taller, that's causing you to weigh more. If you study more, that's causing your exam grades to go up. And a lot of times when there is a correlation, it's because there is a cause and effect relationship between the variables. But that doesn't necessarily mean that there is one. Not necessarily, because the math of correlation is bidirectional. you can say that there is a relationship between two things bidirectionally, correlationally, but that doesn't mean the correlation specifies which way the relationship goes. There could be three reasons why there's a correlation between two variables. A causes B, B causes A, or this thing called the third variable problem. There's this third variable that you didn't measure that is really causing both A and B to fluctuate. And so let's go through some examples. Now, here is a real example from the real world. If I was going to take the days of the year, and I was going to track the days of the year, all year, and on every single day, I measured two things: ice cream consumption by ice cream sales and drowning deaths. What I would see is on any day with high ice cream sales, there would also be high drowning deaths. It's a real correlation. It's not made up. Another real correlation. Ice cream sales is also related to homicides. It's related to all different kinds of gun violence. All different kinds of violence, including gun violence, right? We have, sorry, I'm not an artist, but whatever, right? You have, right, that's my terrible drawing. You actually see that on any day where there is high ice cream sales, there is also going to be higher homicide rates. There's also, on any day with high ice cream sales, there's also more shark attacks. These are real correlations. Higher scores on ice cream sales go with higher scores on homicide rates. Higher scores on ice cream sales go with higher scores on drowning deaths. Does that mean that ice cream is causing all of these things to happen? Is that it? Right? So that's a hard example because let's think of the various possibilities here. Let's think of the various possibilities. Okay, it could be that eating ice cream is causing people to become homicidal. Maybe Ben & Jerry's has a brand new ice cream flavor. Toothpaste and orange juice, which tastes disgusting, which is causing people to become homicidal. Or maybe eating ice cream is causing and maybe also ice cream is causing people to get cramps, which is why there's an increase in drowning deaths. Maybe eating ice cream stays on your mouth, which is why when you get in the water, the sharks are attracted to you. Maybe ice cream is causing all of these things. A causes B. Let's call ice cream A, and let's cause all of these other things B. Ice cream is A, and shark attacks is B. Ice cream is A, homicides are B, right? And I'm saying that A causes B, always. But is that necessarily the case? Because let's think of a different explanation. Maybe B causes A. Maybe people who are homicidal, people who are committing violent acts, are going to eat ice cream as therapy. So B causes A. That's certainly possible. Or maybe after people drown, their family is eating ice cream at the wake. So B causes A. Maybe after shark attacks, people are eating ice cream to make themselves feel better. So ice cream is therapy. Maybe that's the case. Or how about this? Maybe it's the third variable issue. Maybe it's the heat. Maybe it being hot out is leading to increased ice cream sales, increased shark attacks, increased homicide rates, because believe it or not, heat does make people feel pretty aggressive, and increased drowning deaths. Maybe it's the heat. Maybe the heat is leading to all of these things. And that's why, even though there is, in fact, a correlation between ice cream sales and the drowning rate, ice cream sales and the murder rate, ice cream sales and shark attacks, it's not a cause and effect relationship. And so it's important to never overinterpret a correlation. A correlation is a suggestion that there might be a cause and effect relationship, but it's not by no means a certainty. The only way that you can establish a cause and effect relationship is with what's called a true experiment, something we talked about at the very beginning of class. And so the drowning deaths and homicide rate and ice cream example is an easy one. But how about this one? There have been lots and lots and lots of studies, numerous studies, showing a correlation between taking a hormone replacement therapy called HRT in women, people who take hormone replacement therapy at menopause, so estrogen and progesterone, and then their risk of coronary heart disease, it goes down. That if you take this medication, your risk for coronary heart disease seems to be lower. So is there a cause and effect relationship? There is definitely a correlation. Among the women who take hormone replacement therapy, there is absolutely a lower incidence of heart disease. You can track it. Just like you can track on any day with higher ice cream sales, you can bet money there are going to be more homicides that day, more drowning deaths that day. But there's no cause and effect relationship. But what about in this medical example? It's much more difficult to wrap our head around. Because in the ice cream example, you can sort of pretty quickly come to that third variable. It's the heat, right? It's the heat. But what about for this one? Could there be a third variable? Is taking the hormone replacement therapy leading people to have less heart disease? Is having less heart disease leading people to take the hormones? Or is it something else? Well, the punchline is it is in fact something else. And that something else is money. Women that can afford hormone replacement therapy can also afford all other different kinds of health care. They can afford healthier foods because people who live in poor areas who don't have access to hormone replacement therapy often don't have access to fresh foods. It's called a food desert, and many poor folks live in what are called food deserts. And people who have access to hormone replacement therapy also have access to exercise because they can go to the gym. They can afford a gym membership. People who have access to hormone replacement therapy also have access to doctor visits regularly. And so the women who take hormone replacement therapy, it's not the hormone replacement therapy that leads to lower heart attacks. It's those other things. It's a third variable. And that third variable is money. You got more money, you can get the hormones. You got more money, you can go see the doctor, less heart disease for you. That's the idea. Correlation does not imply causation. It's a hint, but by no means a certainty. All right, so going back to this slide. I used to think correlation implied causation, says this comic from Randall Monroe, xkcd.com. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Why is that funny? Because him getting this knowledge and him taking the class is just a correlation. Maybe he learned this in a different class. Maybe he didn't learn it in the stats class, right? Correlation is not causation. Some more theory that we have to learn is there are times when calculating a correlation is a bad idea, meaning the number that you calculate is not a good number. And I'm not talking about cause and effect relationships. That's different. You can calculate a real, meaningful, interpretable correlation that you can bet money on that is not a cause and effect relationships, like ice cream sales and the homicide rate. If you know that on any given day the ice cream sale rate is high, you know for sure that the homicide rate is going to be higher that day. Not because there's a cause and effect relationship, because of the heat. Right? Ice cream sales are only high on hot days. Homicide rates spike on hot days. It's a real correlation. You can bet money on it. But there are other times when a correlation, you shouldn't even calculate it at all. The number that you calculate is just going to be wrong. It's just going to be wrong, 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 wrong. And here are here are 3 times that we're going to go over where calculating a correlation is going to end up an unrepresentative index of the association. It's going to be wrong. The number that you calculate is just not going to be the right number. Cause and effect relationship aside, that doesn't even matter at this point. The number that you calculate is going to be wrong because the data is problematic. It does not represent the real relationship among the variables. And the 3 that we're going to go over are range restriction, outliers, and nonlinear effects. These are the 3 types of problem data that if you see them, you're going to be like, ho, 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 I should not calculate the correlation. And you know you have these 3 problems by looking at the scatter plots. If you see these 3 type of problems in the scatter plots, then you know you should not calculate the Pearson product moment correlation coefficient, affectionately known as the correlation. So we're going to go over the range restriction, outliers, and nonlinear effects. So, And the idea behind this is the data itself is problematic. It's not the kind of data where you should calculate a correlation. You'll need to calculate something else, right? And these are not all the different types of problematic data that are out there in the world. We're just going to focus on outliers, range restriction, and nonlinear effects because they're really, really common, really common. And when you see these kind of scatter plots, you know, I can't calculate a correlation. Sorry. I'm going to need a different number to represent the relationship between these variables, not the correlation. Outliers and range restrictions have a very unpredictable effect on the correlation. Sometimes outliers will artificially increase correlation. Sometimes they'll artificially decrease the correlation. Range restriction as well. Sometimes range restriction will artificially increase the correlation, and sometimes it will artificially decrease it. It just really depends on the variables in question. Bottom line is outliers or range restriction, don't calculate the correlation. Nonlinear effects, however, almost always make the correlation look too small. It is way too small to accurately represent the real relationship between the variables. So here is an example of an outlier, two outliers actually. So let me draw my circle around these cloud of dots. Oh no, but I have these two little outliers up here. Whatever will I do? Because if I circle the rest of the data, it certainly looks like there's no correlation. But then when I have to try to wrap this thing around all of the dots, it makes it seem like there is a stronger relationship than there is. These two little baby outliers up here make it seem like the relationship between the two variables is stronger than it is, when in reality, for 99.9% of the folks, there's no relationship at all. This may be a data entry problem. This may be you are doing research on children and a couple of adults stumbled into your sample. There's a lot of reasons why you may have outliers. But if you have outliers, you can't just calculate your correlation and go on your merry way. You're going to have to figure out what's going on when your correlation is being driven by just two people, when the correlation is as a result of just one or two people. These are called outliers because they're out in the outlands, away from the rest of the data. Here is an example of an outlier artificially decreasing the correlation. If I draw my little oval around most of the dots, it looks like a pretty darn strong correlation. But when I have to try to grab this one outlier, it's going to make the correlation smaller than it would be if this one outlier wasn't here. And so if you have an outlier, a dot that is far away from all the other dots, you can't just calculate your correlation and go on your merry way. You're going to have to deal with it. And in our class, the way we're going to deal with it is by not calculating the correlation, by saying this is an outlier problem. I should not calculate the correlation here. And you can only do that by looking at scatter plots. Here is an example of range restriction. Here we have data that looks like a pretty moderate or medium effect, but I have chopped off anybody with an X score above 0. Anybody with an X score above 0, I've just chopped them off. I have taken the range of X and chopped it away. And so all of these people are lost to me. I've just gotten rid of them. And so it makes the relationship seem weaker than it is because of range restriction. Here's another example of range restriction. This is what is called a ceiling effect, right? This is for whatever reason, there aren't scores on Y that go above 1.5. If I had been able to measure things on Y above 1.5, maybe I would have gotten a nice, beautiful correlation that was much stronger, right? I would have gotten some ranges up here, right? Where I would have gotten a nice hot dog shape. But because I don't have any range of Y up there, it's range restriction. And now when I draw my circle around my data, it looks a whole lot weaker than it would have been if I had had the full range of Y. Now again, I don't know why I have a ceiling effect here. I don't know why I'm seeing data that looks like this. But when I see range restrictions, ceiling effects, or if the data was clustering here at the bottom, it would be called a floor effect, right? For whatever reason, I have this kind of range restriction. I can't calculate the correlation and then go on my merry way. I'm going to have to do something else, and the correlation isn't it. And lastly, here is a nonlinear effect. Essentially, everything that we've calculated where it was reasonable to calculate a correlation, like here, a straight line fit the data well. There was a linear relationship here. Let's erase some of this black stuff so I can show you. Here, you can draw a straight line through the data. It's linear. It's linear, right? There's a straight line type of relationship. Here, it's more like a parabola. It's a U or an inverted U-shaped curve, right? Either way, I could have something that looks like this, like a U, or if I had data that looked like this, right? Here's my X and Y axis, and if I had something that looked like this, that would also be a nonlinear effect, right? Essentially, a straight line does not fit the data well. But you would never say that these two variables are not related. They just don't have a linear relationship. And so calculating the correlation would not be the appropriate thing to calculate. You would have to do something else, and that something else is not the correlation. And a great example of a nonlinear effect, let me draw it for you here. A great example of a nonlinear effect is the relationship between stress and success. So here we've got stress down here, ST, stress. And here we've got success up here. So I'm just going to draw a happy face for success. And let's say it's success in a class. If people have no stress about a class, I said this person A, they have no stress about the class. Well, they're probably not going to do so well because they're not stressed out about it at all, so they're not going to study. Person 2 has a little more stress, so they're going to study a little more, and they're going to do a little better. Person 3 has even more stress about the class, so they're going to study even more, and they're going to do a little better. And on and on and on until you hit this like peak of stress. And then you're going to be performing at the maximum capacity. You're going to be doing as well in the exam as you can. But then if you have more stress, like your dog dies, or you have more stress, your boyfriend or girlfriend breaks up with you, more stress, you get fired, more stress, you have 9 classes, more stress, more stress. There's a nonlinear relationship between stress and success, where when stress, the X variable, reaches a certain threshold, right around here, success starts to nosedive. There's definitely a relationship between stress and success. It's just not a linear relationship. It's a inverted, an upside down U-shaped curve. But if I calculated the correlation, I'd get a big fat 0. The correlation would not be a good representation of the relationship between the two variables because I have a non-linear effect. Now, so that's theory. There is one more type of calculation that we can do with a correlation, and that is combining the correlation with the null hypothesis significance test. Because believe it or not, the covariance and the correlation, although you can interpret them, and they're you can interpret the correlation. The covariance, you can interpret it once you standardize it by turning it into the correlation. Even though the correlation is cool and you can standardize, you can interpret that standardized index called the correlation, right? It is just a descriptive statistic. The correlation is just a descriptive statistic. You can in fact calculate a null hypothesis significance test for the correlation, where the correlation itself is the effect, and then you can divide by standard error of the correlation to ask this question: in the population, is the correlation equal to 0? And the parameter for the correlation is this Greek letter rho. It's not a P, that is the Greek letter rho. I'll go ahead and spell it for you. And so when you calculate a correlation, and then the Greek letter looks like this, that's rho. And so you can take the correlation which is neat and interpretable, but really just a descriptive statistic. And you can do a null hypothesis significance test, right? You can do a null hypothesis significance test on the correlation where you ask this question. In the population, is the correlation equal to 0 or is it not equal to 0? Where the null hypothesis is that the correlation is equal to 0, so there's no relationship in the population. And the alternative hypothesis is that in the population, it is not equal to 0. Because let's say our sample correlation is 0.3. Maybe that's just sampling error. Maybe we just happen to get a sample correlation slightly different than 0. And so instead of looking at averages now to see if they're the same or different, we're trying to decide if our correlation is the same or different from 0. And happily, in order to do that, we can just do a t-test where we use n-2 degrees of freedom, where you put the correlation in the numerator, because that's the effect, and this is the standard error down here. This is the standard error for a correlation. 1 minus r squared divided by big N minus 2, and take the square root of the whole thing. And where you use n-2 degrees of freedom to look up a critical t. So it's just a t-test, where you're wondering, is this r different from 0? Right? So technically it's r minus 0, right? Because this 0 is the null value, right? R minus 0, but whatever, it goes away. You're not going to put 0 on anything, right? And so you use, and that will give you a t statistic that you compare to a critical t. And if you reject the null hypothesis, then you say that your correlation in your sample is reflective of a population correlation that is different from 0. And so if we take our correlation from before, let's go ahead and do that. Remember how we calculated a 0.97? Let's actually do the t-test for that, right? So let's go ahead and do that. Let's do a new slide. Right, and so we'll go ahead and do that. So let's borrow this equation. And we'll take our correlation from before. And so we're going to do a t-test. And how many people did we have? We had 4. So we're only going to have 2 degrees of freedom. So we're probably not going to reject the null with only 2 degrees of freedom. But let's go ahead and see. So we take the correlation, 0.97, and we're going to divide by 1 minus 0.97 squared divided by n minus 2. And voila, I've turned this into text so you don't have to count on my chicken scratches. And now we can just work through this math. We're going to take 4 minus 2, right? And that'll just get, because that's this part of the equation here, right? That'll give us 2. And then we're going to take 0.97 and we're going to square it to get 0.94, right? So 0.97 squared becomes 0.94, right? And now I'm going to take 1 minus that to get 0.06, right? And so now I have 0.06 divided by 2, right? I now have 0.06 divided by 2, which gives me 0.03, right? And now I take the square root of that to get 0.17 after I round. And so I take 0.97 and I divide it by 0.17 to get 5.705. So my t is, my t for 2 degrees of freedom for 2 degrees of freedom, thank you, you're not being helpful, Microsoft, for 2 degrees of freedom is 5.7. Now, you, of course, would show me every single step, right? And so, but that is, well, 0.71. If I round properly. And so that is my t statistic that I would then compare to a critical t based on 2 degrees of freedom, right? Now this was only 4 people, so I only have 2 degrees of freedom, so it's going to be n minus 2. Why is it n minus 2? Because I have 2 variables here. I have an x variable and a y variable. So when I'm looking at the correlation and I want to know my degrees of freedom, I'm going to use n minus 2 degrees of freedom because I have 2 different samples, 2 different sets of I have 2 variables. And so I would look up then a critical t in that table A2 in the back of my book using 2 degrees of freedom. And what I discover is that the critical t crit as your book likes to call it, is 4. Let's see, what was it? So it is 4.303 is my critical t. So in this case, even based on only 4 people, I can reject the null hypothesis because the correlation was so big, 0.97. That was crazy big. And so even with only 4 people, I was able to reject the null hypothesis, which is sort of cool. I would say that in the population, the correlation of 0.97 is not equal to 0. This is not sampling error. And last but not least, remember, correlation is not causation. And when we learn next time about regression, it's going to feel even more like we're implying cause and effect relationships that may or may not be there, because regression is just a mathematical extension of the correlation. And so just like we can't assume a cause and effect relationship with a correlation, we cannot assume a cause and effect relationship with regression. All right, see you next time.